Good afternoon. Thanks very much for coming to my talk. Thank you very much to the organizers of the Haskell Exchange for giving me this opportunity to speak here. I'm working for Tweak.io, and through them for IOHK, working on the Bluetooth language together with Phil Wadler, which is the language on top of the Cardano blockchain, which Duncan told us about earlier today. And you will be pleased to hear it's all based on Haskell, but that's not what I'm going to talk about today. I'm also the author of the Haskell for Mac IDE, and together with Gabriele Keller, the Learning Haskell online tutorial. And this is for teaching Haskell. We wanted something which is a little bit more engaging than just having ASCII characters to play with. And so looking at solutions to graphics programming. So if we think about graphics programming, animation, games in Haskell, we've got a bit of a dilemma. On one hand, there are state-of-the-art game engines, animation libraries, which are typically written in C++, and this particular one, SpriteKit, has an Objective-C API. And, well, of course, we can write a language binding, use inline code, like Facundo explained to us in the previous talk, and then just write Objective-C in Haskell in the I/O monad. Yeah, no? Also, for teaching Haskell, that doesn't sound like a particularly good idea. Or we can do what we like to do in the Haskell community. We can just say, OK, like everything existing is crap. Let's do it properly and start from scratch. And we can start with pixels and start to build up some graphics and have this beautiful, purely functional API. But, well, maybe graphics a little lacking. But that's not because it wouldn't be possible in Haskell to write a state-of-the-art games engine. It's because doing that is a lot of work. And the people who do it, they are specialists, graphics programmers. It's not easy. It's algorithmically knowing the hardware, what you can get out of graphics hardware. That's difficult stuff, right? So kind of redoing all this seems silly, and obviously nobody's doing it if you browse through Hackett for kind of graphic solutions. So that, of course, raises the question kind of, can't we have both? Can't we just wrap an existing game engine somehow in a nice, purely functional API, program on that level, and then have some magic which kind of translates what we do in the functional world somehow down to the nitty-gritty, messy, object-oriented, imperative, other words we don't want to use in this company. So how can we do this? Well, this is what this talk is about, and we'll go in 3 steps. Step number 1, we'll look at what's the kind of thing, what's the kind of thing provided by these existing frameworks. So what's the state of the art? And then we'll have a look at our wish list, kind of like what's the kind of API which would be nice to use for a Haskell person. And then finally, we have to tie the two together. And that's where the tricky bits will be, obviously. OK, so now I want to make it concrete. So in graphics programming, once you want to use a real framework, you have to pick a platform. You have to be a bit specific, because except things like OpenGL or so, which are very low level, or huge frameworks like Unity, things are often not cross-platform. So I've picked the SpriteKit framework, which is Apple's 2D animation and games engine, running on everything from Macs to Apple Watches. And I've picked a small example game as a kind of running example for this talk, which you may find familiar. OK, so let's look at what we want. So this is Haskell for Mac. And you can also, and I'm going to run this code in Haskell for Mac, but we could also generate a standalone app for this program. So the kind of thing we want to do is we have this bird flying along, there's some pillars moving along, there's collision detection, some score. So that's the kind of thing we want to implement, okay? So how can we do this in a system, in a library like SpriteKit? And SpriteKit is quite, it's a very comprehensive system with a lot of features, but its architecture is quite common type of architecture you find in this domain, right? So the kind of techniques I explained, they're applicable to other similar systems as well. So a scene, which is what we just saw, is represented as a scene graph. Well, here it's a tree, and there are various kinds of nodes. Some of them are of a visual nature, such as the sprites. But some of them are just nodes tying other things together, grouping them. But then more interestingly, some nodes, they have actions attached to them. So what's an action? An action could be an animation, like over 1 second, move in an arc over to the other side of the screen. That could be an action. And then some nodes also have physical properties. So they might have, like the bird has a particular weight, meaning gravity affects it. And then the physics engine of the underlying games engine is going to animate things according to the physics simulation that it's going to run on the basis of those physical properties. All right, so that's the setup. And really, it's not a tree. It's a graph because there are all these back edges. But we are going to ignore them for now. So that sounds nice, a tree. That's a functional data structure. So where's the problem? Well, if you look at the types of these things, then, well, each of these different sorts of nodes is actually implemented by a different Objective-C class. And you know, these object-oriented people, they always put these classes in a hierarchy. There on top of this particular one is this SK node class, which is an abstract base class, including some properties which are shared by everything. Every node has a position, a scale, a frame on the screen. There's some methods which are available on all those nodes. Everything else inherits from that. So that's a bit tedious. And then the scene thing, that's the entire scene. It's a subclass of one of these nodes. That seems quite silly. I think it's a really design mistake. For some implementation reasons, they did it this way. But it affects the programs you write, because when you want to write your own game, you have to subclass the thing to get some game-specific state in there. So now we are into subclassing Objective-C classes from Haskell. That sounds like a particularly interesting prospect. And then above SK node, there's another class, superclass, which is a standard class in the Mac OS and iOS frameworks to deal with inputs. And it has all kinds of methods which you have to override in your subclass in order to get mouse events, keyboard events, all these things. So that doesn't look so good, okay? We have to override these event handlers. So that's the first problem. So second problem, well, if you look at this animation again, you see, depending on the vertical velocity of the bird, it changes its tilt, right? So how do you change the rotation of this sprite? Well, welcome back to our abstract base class. It has a property called set rotation, which tells us the rotation. Now, how do we change this? Well, yeah, there's this tree, remember? And the top class object, namely the scene, that class has a function called update. And it's called once a frame to update the tree. And, well, it's object-oriented, so you know instances of this thing have access to a self pointer, which is the root of the tree, and then they just go down the tree, go into this object, and just change the value. Isn't this a weird way of writing programs? So it gets worse, because look, there are these pillars, pipes, and so there are new ones coming in from the right and old ones dropping off the screen. So how do we do that? Well, in this abstract base class, which we've seen a few times now, there's a method with which you can add things to the tree in place, obviously. So, okay, we have this tree. There's a subtree with one pipe pair. Then we side effect the thing to add more children to one of these collection nodes, and another one, and then at some point we also delete some when they go off the screen. I think I have to take a shower now. I mean, this is getting out of hand. So really, we have three major issues here. So on one hand, we have this class hierarchy where we have to override things, subclass things. Then we mutate graphical properties to move things around. And then we have to edit the whole tree on the fly 60 times a second. Well, I said part of the motivation here was to have a library which we can use for teaching. So of course, we could kind of go and say, all right, this is, we use some functional, reactive, free monad, something other, maybe a few dependent types as well, and yeah, but maybe not for Haskell beginner. So really what we want something which is basically Haskell 98, not even 2011, or 10, or whatever it was. Functions, algebraic data types, that's about it, okay? That's a nice, simple API. And in fact, it's a good representation for these kind of computations. So how can we achieve this? All right, so let's start with the whole class hierarchy mess. Well, there was this hierarchy, and I already said putting the scene thing in there, this is just the implementation quirk, so we are not going to worry about this too much. And then, well, it almost looks like a sum type. So let's just make it into a sum type. And so we have a variant for each of the different types of graphical nodes, which can be in a scene. And then the first one, that represents the abstract base class. And all its fields are repeated in the other variants. And remember, Haskell records, for all their faults, have this ability that you can reuse field names through multiple variants and then use them in a more uniform way, which is kind of a way to simulate this abstract base class. But then everything except for the node variant has its own individual node type specific or node variant specific fields which are specific to that particular graphical object. Okay? So that's nice. And then with the scene, we just define a new data type, and it includes a field with a list of nodes as the children of the scene. And also, in order to solve this problem that we have to instantiate these scenes with application-specific information, we parameterize it over two types. And one of them is the basically state which is kept in the scene, which applies to the entire game. And some of it is the information stored in the individual nodes. OK, and then you see like this one appears again as an argument to the node. All right, so that looks a lot saner. And let's use this. So we define, for this game, for this little example, so we define a data type for the state used, additional state used in the individual nodes. All we need here is we need some way to get at random numbers in order to have the pipes happen at different places. And so we just supply a lazy list of random numbers and a way to consume it. OK, so that's easy. And then we need a game state that's a little bit more involved. We have to store things like the score, the current score, some information about input actions and what the state is. Is the game over or still running? That kind of stuff. And so we put those together into the scene type. And then we can start, after we've defined our types, we can start with some code. So we instantiate a sprite node using some smart constructor, and then just updating the record fields which we want to modify from what the default values are, putting the bird at a particular position, giving it a name, lambda, seemed appropriate, and attaching some actions. So those actions, there's basically a little EDSL, if you like, of actions and composing of actions. So for example, there's a way to sequence actions, have actions running in parallel, have actions looping, and so on. And then one of the primitive action types is to give a list of textures and cycle through them in a particular interval. And that's what we are using here. And so we put the bird into the overall scene. And so that's the second data type we saw. We define a particular background. And for now, there's only the bird in the scene. Now, if we look at what that looks like we see the animation cycling through the textures as the flapping of the bird. All right. So that was number one. Not too bad. So how about these mutable properties? Well, we kind of made our choice here. This node set rotation, that's one of these fields which is repeated in every variant of the node data type. So that's immutable. We can't just side effect it or anything. So let's look at this update function. So the way we realize it, we put it as a callback into the scene data type, but we make it a pure function. So if you can't read this because you're in the back, it says scene, arrow, time interval, arrow, scene. So it gets a scene, information about how much time passed, and then returns a new scene. It's a pure transformation function. No IO, no ST, no nothing. OK. So, all right, and we handle events the same way. So in the same way as we have an update callback, we have an event callback, and the event type takes an event, can be key press, mouse event, whatever, the scene data, and maybe returns a new value for the scene data. Again, a pure transformation function. No side effects. All right, so how can we use that in our little application? Well, for the moment, the bird is a little helpless, so we want to add some ability to give it a little bit of lift. So we add an event handler, which whenever we have a key down event, notes that in the game state by changing the game state a little bit. And then in this update handler, so this is this function which is executed 60 times a second in order to update the scene. Now what we are doing here, as long as the game is still running, if a key was pressed, we call this function bump lambda. And bump lambda affects the physics properties of the bird by indirectly calling another function, which we call tilt action. And it takes the physical properties, namely the vertical velocity of the bird, and determines what the new rotation is supposed to be, and just does a record update on that field. So it's going to give us a new version of that node representing the sprite with the rotation changed. Okay? Pure function. And very straightforward, exactly what we want to express here. So with that, now when we press space, we can kind of help the bird not fall off the screen. All right. So how about the third thing, editing the graph? Well, it's actually quite similar. So in all the nodes, the scene, but also all the node variants, carry this list of children. And the way we change the scene is just doing a tree traversal, updating those fields in the tree. I mean, it's like any other rows tree setup in Haskell. Given this interface, so the way we can use it, for example, to introduce these pipes, so here we haven't got any pipes yet, so we add some code which creates a new node which doesn't have any graphical properties. Remember the dotted squares in the tree, which were just grouping things together. And we define an action on this thing. Now, this action is a special action. First of all, it uses the combinator to have a looping action, something which happens over and over again, calling some custom action, which we can define ourselves, waiting for 1.5 seconds, starting from the top again, and so on. So every 1.5 seconds, we will get a new pair of pipes coming in. And so what do we do in this custom action? Well, we call this function spawn pipe pair, which gets the parent node of all these pipes, it's just a node, and then it takes the children, current set of list of children of that node, and just consists another node, being the parent of these two new pipes, in front of it. So again, we have a normal record update, transforming one data structure into another. No side effects, nothing. All right, so that's fine. So let's see how that goes. So now we have these pipes coming in. And so that was easy. I mean, this is basically the kind of code we want to write, right? It's really the most straightforward way to express the kind of operations you want to do in this little example game. And it's the kind of code you can teach even to kids. So I use this to teach my son Haskell. And so it's totally accessible. That level of Haskell, totally accessible to children. All right. But there's always a but. You know, if you read a fantasy novel or a movie where people use magic, usually whenever they use magic, they have to pay a price. This seems pretty magical, right? We do these nice pure transformation functions, and supposedly there's this ugly little imperative engine underneath which somehow plays along. So how do we make it play along? Well, let's think about what's happening here. So with this update function, let's say where we add a new pair of pipes, we've got this tree. Well, now we want to, that's in Objective-C, representation in the Objective-C heap, right? Now we want to apply this pure Haskell function. Oh, well, we marshal from Objective-C to Haskell. That's not too bad. Then we call this spawn pipe pair function, which kind of edits the list of children here to add a new one. And voila, we get a new subtree. What about the old subtree? We just took this thing from Objective-C land, marshaled to Haskell, back to Objective-C again. We are going to do this 60 times a second to get a kind of semi-real-time game going. Does that sound like a good plan? No. It's worse. Why is it worse? Well, actually, let me get back to this slide. So the reason it's worse is because of the stuff hanging at various nodes. For example, the bird, right? Remember the flapping? I mean, something in this system has to iterate through those textures. Remember, what's the current texture? It's going to change every 0.1 seconds, meaning there are multiple frames before the change over to the next texture. So there has to be a counter of how much time has passed. When is the next change of a texture going to be? Where's all this information stored? OK, I told you it's written in Objective-C. Well, actually, the underlying code is written in C++, which really doesn't make it any better. So what do you think these people are doing? Well, they, of course, put some local state into some objects, updated all over the place. And we just took this data structure, the public part of the data structure, converted it into a Haskell value, and then created a new version with only this public information. All information about progress of animations, information about physics will be lost at that point. You get stuttering animations, resetting animations. I mean, it's going to be a complete mess. So this is not only slow, it actually doesn't work. And it's slow. So let's look at what magic incantations we could invoke and pay a price. All right, so remember, we have got the scene update function. That's its type. It's a pure function, gets a scene, gets a time interval, gives us a new scene. And that's representing this whole thing. Now, when we marshal this over, we don't know what we need of that scene. So let's do it lazily. We are Haskell people. Somebody was asking in this discussion yesterday, what can you use laziness for? Well, that, for example, I don't think it's one of the standard examples of using laziness, but it's pretty convenient. So we kind of lazily marshal that. I'll tell you how we do that in a second. Then we apply this pure function, get a new version of this value, and then we want to know what changed. So somehow we have to figure out only what are the changes, and then apply those changes as side effects to the underlying Objective-C data structure. If this reminds you a little bit of things like virtual DOM in React and so on, then yes, you're on the right path. Same idea. All right, so let's look at how we do this. All right, so we've got this tree. Lazily marshalling means we only marshal what we actually consume. So first of all, we just take the first topmost node. We marshal this into a Haskell value. And then we don't want to touch its children. Instead, we are going to put a thunk here, which is a suspended, not evaluated computation. That's the whole point of laziness, operationally speaking. So, and it has pointers to these nodes in case we want to also marshal them. And we do the same thing for all the other fields in that record. Okay? So we don't marshal the name. We only remember a particular piece of code which, when we run it, will marshal the name over from Objective-C. So how could we implement this in Haskell? So if there are any children in the room, could you please turn around? So that's how we do it. So, well, I will not speak of this. If you've been in the last talk here where Facundo explained everything about these inline libraries, well, that's using inline Objective-C. So everything here is actually Objective-C code inline in the Haskell code. But we only want to run it if somebody actually, I mean, in the Haskell world, uses this value. So we wrap it in unsafe perform IO. It's going to be suspended. But if you touch that field, it's going to be evaluated. This Objective-C code will run and give you back the string, just like magic. So that's how we do this. And, well, dealing with the children of nodes becomes even a bit more involved because they can be changing their ordering and so on. So we have to kind of take care there. OK, so this is point one. But we've got this lazily marshaled record value. And then there are all these things in there. We call the update function. And it's going to produce a new copy of the value. And let's say we just changed the name. Everything else we did not touch. How do we know? Stable names. Somebody said stable names. Well, the problem with using stable names here is stable names is something you apply to a Haskell value. So we could kind of wrap everything, but I mean, if you look at the type here, the type of this thing was string and not stable name of string. And putting stable names everywhere would make the API quite strange, and you have to use I/O to create them and so on. So we want a bit more magic. Okay, Andres is on the right track. So what we are going to do, well, we are just going to compare these fields using something even worse. So don't use this function. I mean, it's in the name, right? It says don't use it. Also, anything with a hash mark in the end, no, really don't use this. I mean, don't, okay? I've got a special license. So what we are going to do, we are just going to do a pointer comparison here. I mean, if something touched that name, remember, it's a thunk, then it's going to be evaluated, and because we are not just called by need, but a lazy language, there will be an update to that thunk, overwriting it with the result of the evaluation, different pointer. Okay, so that way we figure out whether it's still the same, or do we have to use some inline Objective-C again to update the name in the Objective-C representation of that object. Okay, that seems pretty bad. Now you may wonder, it got worse. What's the third one going to be?
It didn't improve safety.
No, yeah, I need a third mechanism.
Unsaved.
Oh, we already learned in this conference that using coerce is totally okay. You use it all over the place in about every library you can think of. No, it's a total letdown. We use maybe. Oh, that seems okay. I mean, every node actually, every variant of a node actually got a field called node foreign. It's called node foreign because if that node originated from Objective-C, so it was more marshaled over from Objective-C and not just created Haskell side, then it contains something of type SK node, and SK node is a foreign pointer, hence node foreign, a foreign pointer to the Objective-C object instance. That seems very harmless. It's worse than the other two things together. Why? Because this is just a normal field in the record, right? So what prevents you from making a copy of the thing? Throwing it away, throwing away is no problem, but you could make a few copies. So how do we use this? Why do we need it in the first place? Well, think about it. We've got this one tree and the new tree, and modifications sometimes will be quite far down in the tree. And maybe some of these lists of children in between in that path have been permuted, or some entries dropped, some new entries coming in. Then we still have to be able to figure out what is the corresponding Objective-C object where we have to do the update if we detect a change. And to figure that out, we really just in that Haskell representation have to have a pointer to the Objective-C version to know that's the one I have to update. So now if you copy the thing, then there are two Haskell representations for the same Objective-C thing. That doesn't seem like a good plan. So the library is conservative. It basically, whenever you copy things, I mean, whenever you create new nodes of a type, it means a new node is created. And that happens all the time. With the pipes, for example, we just added some new nodes. But they had no Objective-C corresponding thing. So that's fine. So if we encounter multiple of those, then we just treat it like you wanted to create a new node. And that may or may not be what you wanted. So it's not so nice, but it's also not a real semantic problem. But it shows that once you deal with these foreign objects, you're on shaky ground. Okay, so that's the 3 ways in which we had to abuse Haskell. But the point is that this is all inside the Haskell SpriteKit binding. So this is like systems programming. I got my license to do systems programming. I go into the swamp. I deal with the unsafe whatevers and the hash marks, so that on top of that, we can have a nice, purely functional, actually very simple API to use an advanced game engine quite nicely. So if you want to know all the gory details, well, it's all on GitHub. In fact, there's a link to a paper which has some more details, another example, and so on. And all that code is also linked from that GitHub page. OK, thank you very much.
I think you first. Thank you. Wouldn't it be possible to replace the pointers with IDs and have resource pooling in the imperative side?
Well, so the question is whether we could, instead of using actual pointers, use a table and then use indices into that table. Yeah, sure.
Because that would save this unsafe layer from your system.
Yeah, you still have this, let's call it semantic mismatch, where by duplicating something on the Haskell side, which then duplicates a pointer into this, an index into this table, you don't know. So if somebody, for example, copied this thing because they wanted a second version, that happens a lot. Like you have an object in a game, something happens to it, and it kind of duplicates. So you can implement this by just duplicating the thing, and that's it. What you should really do, whatever is the new version, you should put nothing into that particular field. So if you don't do that, the graphics engine has no idea to know which one is the original, which one is the new one. So it'll just pick one, which may be the one you wanted or not. That means any animations running on the thing, for example, will run on the one that the engine picked. And maybe you wanted the animations on the other one. So that's the type of thing which can go wrong. Yeah, what I forgot to say, by the way, tying in with the first keynote, so this is another place where linearity would be good. Because if we can guarantee that these fields are used in a linear way, we are safe. So that's another way where linear types could make previously unsafe API safer.
Can I ask about memory management? How do you not leak memory magically?
Memory management for
who? Because
Haskell
you create a lot of objects, right?
Oh, OK. The usual thing, we just use finalizers, and it's just use standard FFI stuff. So for all the references to foreign objects that we import into Haskell land, we have a finalizer. Objective-C uses a reference counting garbage collection scheme. So we make sure to account for those references. And then when the finalizer runs, we call the corresponding function to decrease the reference. So may not go down to 0, but that there are no more counts in the under reference count from the Haskell side. So
because I wondered, how does it influence the frame time? So can it happen that like garbage collector will accumulate them and stop you midway?
No, because so the Objective-C side deallocation happens immediately. So the way the Objective-C memory management is implemented is that once the reference count drops to 0, it immediately deallocates the object. It doesn't do any scanning or anything like that. So yeah, and it's really the same situation. If you write the corresponding Swift code to write a game, you're in a similar situation. And yeah, usually when you do this, one trick on the Haskell side to play is always a good thing to do is when you are basically at a moment where you know you have some time. I mean, you don't mind a little pause. It's always good to call the gc collect function so that you have a little bit more of control when the Haskell side collections happen.
This is a bit of a strange philosophical question rather than Haskell-y related, but I build lots of games for a living, and the stateless stuff sounds really fun and it's really relevant to what we're doing. But part of when you're making a game, it's quite nice when the code relates to this weird world that you're making, and it feels like throwing away the world every time anything changes. And it's almost like that philosophical thing of, have we just been put on this world with the memory of the past, and we're constantly new things? Like, does it sometimes when you're coding, is it nice that the object-oriented one seems to make much more sense for the thing that you're actually making, because there is a state, there are real objects, you're changing properties on them. Does any of that fall into place when you're actually coding games with this Haskell kit?
So I think it's a matter of what perspective you take. So the perspective I like to take is similar to the perspective that FRP programs take. We reify time. So I'm not thinking about the world at the moment, I'm thinking about the timeline. And then a transformation function gets me from, it's like you put all the individual frames next to each other like on a film, and then the transformation function is what gets you from one frame to the next in your film. And that's how I imagine it. Does that?
That's a really good analogy, yeah.
Thanks.
So with this trick for using really unsafe pointer equality, it seems that you're trying to find out whether things have changed, but what you're actually finding out is whether they've been read. And does that matter? Do you end up potentially doing a lot more extra marshalling if you've maybe queried some property deep in the scene graph but not actually changed anything?
So the amount of work you have to do is in proportion to the amount of change. So for example, the update function, I mean, it gets the root of the tree. So if it wants to change something down in the tree, well, it has to traverse the tree. Now when I do the diffing and applying changes, the diffing algorithm has to do the same amount of traversing as you did in your update function. So that's why I think it's okay, because sure, if you change everything, then the marshalling will be slower. But it also means you have to do a lot of work on the update function. And sure, if you put too much into the update functions per frame in any library, animation library, you'll get stuttering and all the bad things. So that can, of course, happen. But I think the important property here is that the amount of stuff, of data we touch during marshalling should be linearly in proportion to the amount of data touched by the actual update function, by the logic of the update function. Does that make sense?
Yes, I think so.
Okay. Any more questions?
You mentioned React with the virtual DOM. When you started programming the SpriteKit, did you start with the idea from React in the back of your mind, or did you naturally arrive at the same algorithm?
Yeah, no, so I learned about React afterwards. It's basically the premise really was, how can we, because obviously we don't want to represent the mutation itself in Haskell, because I mean, once you have actual mutation, like from this API you provide in Haskell, then you need to use either I/O or FRP. You need to use one of these mechanisms which we use for dealing with state changes, right? And that automatically gives you a much more complex API. So the question was really, how can we relate the two behind the scenes without without exposing it in the API. And there's one fundamental difference to how SpriteKit does it and to how React works. React actually has these functions which always produce new versions of the rendered objects. Whereas here, we really do this lazy marshalling in both directions. So although it's conceptually similar to what React does, actually React works still quite a bit differently. But I think, so React is one example. There are other examples. I think this is actually a little bit of a principle, I think, a way of wrapping unsafe big data structures in a more functional API. This idea of having a virtual representation and then figuring out changes automatically and pushing them down to the underlying representation. And React and SpriteKit are really two instances of that, and there are some other libraries as well. So I think it's interesting to consider it really as a particular architecture for these sort of foreign language interfaces.
We have to stop here. So let's thank Manuel again.
Thank you.
And please remember there will be